Good afternoon, everyone. My name is Jiansong Zhang. Currently associate professor at Purdue University. So today, the title of the presentation is implementation of robotic manipulator end-effector construction automation. But what I really want to show is the bigger context of this work, because this is just one piece of that, right? And the authors, the first two authors, Aarón and Arturo, are two undergraduate students from Mexico, the technological monetary, and Professor Ruiz, Félix-Herrán was their advisor in Mexico. So this specific piece here was based on collaboration between Purdue University and the technological monetary university. So there's an MOU between our university there. To provide a bigger context for this work, it was actually a National Science Foundation Partnership for Innovation project that we launched back in 2018. So there are two themes in this project. One is on the automation of building code compliance. The other will be the automation of construction using robots in the context of modular construction especially. So we do collaborate with the government agencies such as the Building Commissioner of Indiana, which is part of the Department of Homeland Security, and we collaborate also industry companies like Smart Review, which is it's like a tech company, it's a startup professor in California for quite some time now. So they actually have their system to perform the automated code compliance based on Revit models. And we also collaborate with Indiana Construction Roundtable, which is a nonprofit organization. And of course, from the academic side, we collaborate with University of Illinois Civil Engineering Department, and various schools and departments at Purdue University, but especially from the mechanical and robotics side. And we also work with the healthcare industry, such as Kaiser who have been very supportive of the code compliance research as well. So that's the background. For the motivation of this work, we probably all know there is a workforce shortage problem pretty much across the globe. It's also very intense in North America. In the US, for example, 80% of the companies are facing difficulties and challenges in filling their tradespeople, trades positions. Another motivation is the safety concerns. We have seen some very nice presentation from Polar that looks into the interaction between robot and human. So safety is another very important issue in the construction context. Obviously, last but not least, the slow speed to adopt the automation in the construction industry in general, which have caused the productivity of our industry to be stagnant for many decades. So this was one of the initial work that we actually looked into how we may use the interoperable building information models to support the simulation of using existing robotic systems such as industry robotic arms in pursuing some construction tasks and operations. For example, the figure 2 on the right-hand side is a demonstration example in case of the timber construction. We just try to put together this timber frame with studs, and then the robot also can carry nail guns to do the nailing, etc. So from figure 1, we can see on the left-hand side, there are two major inputs. One will be the beam design, which will be in the IFC, Industry Foundation Process format, because it's more interoperable rather than proprietary format, although it's not totally interoperable, which is another topic. And the other inputs will be the robotic system, whatever existing robots we may already have in the market. And through the simulation, the simulation will be generated automatically using our methods based on the logic programming and logic reasoning. And then the automatically generated simulation will help you analyze what are some of the challenges and limitations of using existing robots in this specific construction operation. And then based on the limitations that we have analyzed and obtained from the previous past, we got the idea of how we may actually improve the robotic system to make it better tailored for those construction operations. So we actually ended up developing a new robotic end-effector that combined multiple operations into one device. And we patented this, so you can see the US patent if you're interested in reading the details. This was the patent number. So obviously the next step for patent is to potentially commercialize it. So we have been talking to some startup companies, and they would like to see a physical prototype. So that's what we have been working on. Based on the robots we already have, just we have easy access to these KUKA robots in our lab. So we try to develop the physical prototype of our newly patented end-effector that can be combined with this existing robotic arm. So figure 5 is the methodology in developing the different components of this physical prototype. And then figures show some of the components in terms of the design of them and the actual physical production of the prototype parts and pieces. So this one specifically, we're looking at a pneumatic system, which is critical in terms of if you want to, first of all, grab that, whatever timber piece. In this case, we're mainly looking at like panels or drywall sheets, things like that. So there are suction cups, as you can see on the 4 corners, and you can use the suction cups to carry that panel. And on the right-hand side is stress analysis that we have used finite element models to try to analyze in terms of different posture, gesture, and movement, what is the load capacity, right, for this design. And then the students were very creative. They actually use 3D printing to print the parts and pieces. We primarily use the plastic material for the 3D printing of the very first prototype. In fact, just a couple of days ago, we broke this first prototype because the material, the strength of the material is not ideal. The load capacity was limited, right? So we broke the first prototype. So the next iteration, we will need to use slightly stronger materials. And I think eventually we may need to go to the metal materials for those parts. And figure 11 shows the elbow joints assembly that you can see a clear view on the figure 13. So the, starting from these suction cups, which primarily carry this panel. You imagine the panel here, and we have several degrees of freedom that can help you manipulate that panel, and then at the end of the arm, you can carry different machines like a nail gun to help you with the nailing operations. Yeah. All right. So very quick and short introduction of this work. So to conclude, we have developed a physical prototype of a patented robotic end-effector for construction automation. And our method, including the interoperable beam for automated generation of the simulations for the construction operations, can provide better physical visualization. And we can also support integrated understanding and physical evaluation of all the components, hopefully through this physical prototype. We also already started implementing the control electronic and vision system. So Hui Guang, the earlier presenter, has presented some very interesting algorithm for the computer vision-based system to guide the robots. So it's a similar idea here. And then we will test the system for iterative refinement. And to acknowledge the support of our school construction engineering technology at Purdue University has provided quite some logistic support in this work. Also acknowledge our colleagues, Dr. Jose Garcia Bravo, for access to the 3D printers in their lab with the 3D printing process. Dave Polterman at the Beauty at Scale Lab for providing the manufacturing equipment, as well as Rosita Lopez, our lab technician. So these are the references. Thank you very much for your attention.
Thank you. It's a very interesting approach. For the next, we're gonna have the Q&A after the next presentation. So for the next presentation, I would like to invite Rich.
Yeah.
Yeah, Rich. You're from Hong Kong?
Yeah.
Yeah, from University of Hong Kong.
Yeah. Hello everyone, I'm Rich from Hong Kong the University of Hong Kong, and my presentation is mainly about the low center of gravity movements robotic arm with kinematic optimization algorithm for on-site construction. So firstly, I want to introduce why we propose this topic. And firstly, in Hong Kong, we are many pay more attention about the module integrated construction, and you can see there are two phases. Two phases. Firstly is the on-site phase, and another is the outside phase. And so we built the module in the factory, and so how to assembly this module in the real on-site construction is a problem. So right now there are many problems for the MIC. So about explosion to substantial risks, and also low controllable quality. So we want to introduce the robotic arm to confront this complex problem. But right now the cases for the robotic arm are mainly based on the weld or aerial platform or the scaffolding. And so these are not suitable for the construction arms. And the construction arm, firstly, is too large, and also they need very high adaptation of the complex environments. So we try to fix it on this frame. So we personally propose the 4 arms on 4 edges. So next step, how to control it. So we will simplify the module. So the robotic arm is mounted on the platform, which is under the existing power crane. So while this robotic arm is operating, and is male swinging and due to the center of gravity CLG movements. So how to solve this problem? So is we mainly focusing on the to lower the CLG movements. Firstly, we consider it about 6 industrial robotic arm, like the left figure, and one fixed targets. There are only 1 or 2 kinematic solutions. So we want to try more for this one, and we analyze the doors and want to add a joint to this robotic arm configuration, and we named it as gravity control marine robotic arm CLGCM. And so we have a paper about not submitted. Is about which joint to add this joint is suitable for the gravity control. And so we need to firstly to control this CLG movement. We need to modeling the CLGCM robotic arm. So we use some transformation metrics and to assume every link is rigid, and so we can get the CLG position of this robotic arm. And then so we divided it into a discrete state space function, and as we all know, the robotic arms control of this is we send the command, and the command is discrete. So mainly based on the discrete state function is very helpful for the control. So and then we further simplify this state function. So for every joint, it have three states. First is the clockwise rotation, and the low rotation, and the counterclockwise rotation. So there are three states, and for each state have a very small resolution. So we have the objective function is contributed by two parts. First is the endpoint of this robotic arm. We need to make it to the endpoint, and the second is to control, make that the CLG movement is very small. So there are two requirements for this algorithm. Firstly is to solve the complex problems. As you see, the CLG function is very complex and with many parameters, and then is predictive. But because to come to the endpoint, we don't know which step, how many steps will let this robotic arm to this endpoint. So it's need to do a predictive capability. So right now, the model predict control MPC is very suitable for this control, and it contains three steps. First is prediction, and then optimization, and the last is implementation, and also do the receding horizon. But this MPC is also too complex for formulates and to solve this problem. So we like to have another method to solve this problem. Firstly, and assume we have a horizon length L, and we can obtain the theta hat and to the time t to the plus L step, and we can use some any optimal algorithm to solve this problem. And after we obtain the theta hat, we can have a solution space, and based on this time t and the time t plus L, we have a solution space that's down left this figure, and the theta hat t plus 1 minus 1 t plus L minus 1, they must exist in these two circles. So we can reduce the solution space, and to find the next step, and to similar to step 2, and we step by step to find the theta hat t plus 1, and then implement the t plus 1. So this is the experimental results, and the blue line is the center of gravity, and you can see. Sorry, it's not. So you can see the center of gravity is moved in very short or direct space, and to the sixth of robotic arm, it is also moves more smoothly and more direct and in a short space. And due to the time limit, so I only do some simulation about it. And right now I'm do some physical experiments on it, and we have designed a new configuration of this robotic arm. Okay, thank you.